So I always hope that nobody watches my practice test videos, that you try to complete the practice test by yourself before watching the videos. You check all the answers, you look at the solutions. If you have everything right, then there's no need to watch this. Hopefully, maybe you got one or two problems that you didn't quite understand and you just fast forward to that part of the video. So I move at a little faster pace on the practice tests, specifically because I'm hoping that this is just for me and nobody but me. So the first four problems really come out of section 5.1. They want me to do just some basic indefinite integrals, which means I need a plus c at the end. And this first integral of 8x cubed, I wrote down or typed up saying that the first thing I need to do is pass the 8 through the integral. That's what that rule that I have on the screen tells me that I'm allowed to do. Now I'm going to use the power rule to integrate. And when I integrate an indefinite integral, I need a plus c at the end. And when I use the power rule, that implies I have an x to some power that's not -1. I add 1 to the exponent, so the new exponent's going to be 4, and I multiply by a fraction that has 1 over that new exponent. In this case, it's going to be 1/4. And now I just simplify this up the best I can. Cancel the 8 with the 4. The 4 becomes a 1, so I don't get a fraction anymore. The 8 becomes a 2. And I'm left with 2 times 1 times x to the 4th. The 2 times 1 is 2. The x to the 4th stays x to the 4th. And then I leave my plus c. And that's it for problem 1. Problem 2 wants me to integrate a polynomial. So I need to separate it into multiple integrals. In this case, I'm going to separate this into 3 integrals using the rules that say if I have adding or subtraction within an integration, I can separate a single integral into multiple integrals. So the first kind of hint that I said is, let's make this into 3 integrals. The integral of 8x cubed dx minus the integral of 6x squared dx plus the integral of 5 dx. Then I suggested passing the coefficients out in front of the 2 integrals with the x's. So I'm going to make the first integral 8 times the integral of x cubed dx, same integral from problem 1. Second integral minus 6 times the integral of x squared dx. And the last integral is a constant. I'm not going to move that 5 out front. Now I'm going to integrate. The first two I'm going to use the power rule by adding 1 to the exponent. The last one's a constant, and the integral of a constant, you just take that constant times x. So first integral, power rule, add 1 to the exponent, multiply by 1 over the new exponent, bring down my minus sign. Second integral, add 1 to the exponent, multiply by 1 over the new exponent. Last integral is a constant, it's just that constant times x, and then plus c at the end. Now, same canceling for the first canceling as problem 1. Second canceling, 6 and the 3 cancels, 6 becomes a 2, the 3 goes away. No canceling for the last piece. So all my fractions are gone. First term is 2 times 1 times x to the 4th, that's going to be 2x to the 4th. Second, 2 times 1 times x cubed, that's going to be 2x cubed. Third doesn't have any rewrite, it just stays a 5x. And the last is my plus c. And that's it for problem 2. Fractions usually lead me to use substitution, but that's fractions that have binomials or trinomials in the denominator. Here, this is just a fraction that has a monomial in the denominator. I'm going to first rewrite it with a negative exponent. So I'm going to rewrite this as 4, and then that positive 3, when I rewrite it as a negative exponent, it's no longer a fraction, but that exponent becomes negative. So the rewrite of this is 4 times x to the negative 3, the integral of. Now I'm going to pass the constant, make it in front, or pass the coefficient out front. And now I'm going to use the power rule. I'm going to add 1 to the exponent, and negative 3 plus 1 is going to be negative 2 for the new exponent. Technically, I'm supposed to multiply by 1 over negative 2. Having that negative in the denominator is not my friend, and the fraction negative 1 over positive 2 is equal to the fraction 1 over negative 2. So when I show the multiplication part, that fraction part, I'm going to multiply by negative 1 over 2, which is equal to what I would have written a second, had I not thought about this ahead of time. So I added 1 to the exponent to figure out what the new exponent is. I know I need to multiply by 1 over the new exponent, but that negative messes me up, so I moved it up front. And now it's going to make the simplifying easier. So this 4 and this 2 cancel. 4 divided by 2 is 2. 2 divided by 2 is 1. Fraction is gone. Now I'm going to go 2 times negative 1 and get negative 2. X to the negative 2 plus c. And now I'm going to undo and do backwards like I did on step 1. On step 1, I made the fraction into a negative exponent. On this final step, I'm going to make the negative exponent into a fraction. By leaving the 2, just like the 4 was up in the numerator, this minus 2 is going to stay up in the numerator. And an answer for question 3 is going to be that there. The difference between question 3, which looks structurally the same as question 4, is the exponent on the denominator. When you have an x to the first in the denominator, it's going to integrate to a natural log. X cubes, the only exponent in the denominator that would integrate to a natural log is an x to the first. Problem 4 is going to be a natural log problem, as opposed to add 1 using the power rule, adding 1 to the exponent and multiplying by that fraction. So I have to think of problem 4 with an exponent of 1 in the denominator. And I'm going to do the same business now. I'm going to rewrite this with the negative exponent. That's what the first step told me to do. These steps aren't going to be given to you. These steps are just there just in case you need some prompting. And if you're making a note card, and if you know the steps that you need, try to cram them in. Second step, pass the constant out in front, or the coefficient out in front. Now, the integral I have needs the ln rule. The negative 1 exponent, you don't use the power rule, because if you use the power rule, you'd get an exponent of 0, and that fraction that you multiplied by would have a 0 in the denominator. It would be undefined. So now I'm just going to apply the ln rule. Negative 1 exponents give me the ln when I integrate. And that doesn't even need a rewrite. That's just the answer. Now we're into a series of the use substitution. So that takes us out of 5.1. Now we're in section 5.2. Still indefinite integrals because there aren't numbers on the integral sign, so I still need a plus c in my answer. Basically, there's two kinds of problems that we use substitution for. E problems and parentheses with exponents. This is the parentheses with exponent version. So what I did, I'll just be consistent with myself. You can get to the answer not following these steps perfectly. If you learned how to skip around, that's fine. But I'll be consistent with myself. So my first step, when I have a parentheses with an exponent that I'm asked to integrate, is to rewrite the problem so that the parentheses with the exponent is first. Done with that. Then, I always in a parentheses with an exponent problem, let u be the inside of the parentheses with the exponent, without the parentheses, without that exponent outside the parentheses. So u is going to be that x squared plus 5, done with that step. Now I rewrite the problem so the parentheses is changed to a u. So this is going to be u squared times 2x dx. Now I'm going to find this derivative and use it to replace this. In fact, it'll either come out exactly, or I'm going to have to multiply by a fraction or multiply by an integer. So I'm going to take the derivative of u with respect to x, and on the left-hand side I've always written du dx. On the right-hand side, x squared has a derivative of 2x, 5 has a derivative of 0. If you got comfortable skipping this middle step here and going straight to the step that's needed, that would be better than what I'm just showing right now. If you went from u equal to x squared plus 5 to du equals 2x dx and didn't show this multiplication by dx, that's a good thing. So I found du dx, I multiplied by dx to clear the fraction, and now I'm going to replace. I'm going to take this 2x dx and replace it with du. So that's found du dx, multiplied to clear the fraction. Now let me make the problem only have u's. This is going to be u squared, and 2x dx I'm going to replace with du. Now I'm ready to integrate. I'm going to use the power rule. I'm going to add 1 to the exponent and get a 3 from my exponent. Multiply by 1 over the new exponent, which is 1 over 3. Tack on my plus c. Now change the u back to x squared plus 5 to get my answer. So this is not negative 1/3. I don't know why I have a negative there. It's positive 1/3. Maybe I was trying to write an equal sign and I didn't quite. Oh, there is an equals there actually. I should always write equals if what I'm writing is equal to the line above it. So that's an equal sign that I wrote over, started to look like a negative sign. So for my answer, I'm going to need a parentheses when I change the u back to x squared plus 5. But the shell of my answer is right there, just with the u changed to x squared plus 5. That's the easiest kind of u substitution because this matched perfectly, the derivative matched perfectly what was left. The next problem, I think it also matches perfectly, but they don't all match perfectly. So the two kinds of u substitutions we get are e problems and parentheses with exponents. This is an e problem. If I have an e problem and the exponent isn't just 1x to the first power, then I use u substitution. First step, again, this is just my preference. I think it makes it easier to follow, is to write the e piece first and the piece that I'm going to need to get rid of second. So there's my rewrite with the e first. Now I let u be the exponent of the e. So for u substitution, the u is either the parenthesis, the exponent of the e, or the inside of the parentheses. We did nothing else other than that. So now I can rewrite the problem so that the exponent is changed to u. Now I'm going to do all the work with du dx to get rid of this 15x squared dx. Specifically, I start with my u. I take the derivative with respect to x. The derivative of 5x cubed, I just do 3 times 5 and get 15. I lower the exponent by 1. And then I multiply by dx to clear the fraction. Hopefully a lot of you are going right to this step and doing the multiplying kind of without even showing the multiplying. So now I can rewrite the problem so it only has u's. So this 15x squared dx, I can replace it with just a lonely du because du is equal to exactly 15x squared du. Du is equal to 15x squared dx. Now I use the e rule. The e rule basically says if you have an exponent of 1 times a variable to the first power, that it is its own integral. So the integral of e to the u du is just e to the u plus c. The e rule is the nicest rule. And then change the u back to get to an answer. The u needs to be made into 5x cubed. So for an answer, I change that u back to 5x cubed. The exponent works as a parenthesis, so I don't really need a parenthesis there. And there would be a perfect answer for number 6. 7's another parenthesis with an exponent problem that it's an indefinite integral. I'm going to use u substitution. I'm going to write the parentheses with the exponent first and the 6x dx second. always in a parentheses with an exponent problem. I let the u be the inside of the parentheses with the exponent. Now I'm going to rewrite the problem so it doesn't have the u, or so it doesn't have the parentheses with the exponent. Write it with a u. And now I'm going to use this u, take its derivative to get rid of a 6x dx. So the derivative of u, I can write du dx for. The derivative of x squared is 2x. The derivative of 5 is 0. Multiply by dx, and I get du equals 2x dx. And I say this isn't good enough. I need to multiply to make a perfect match. To multiply to make this a perfect match, I multiply by 3 and by 3. This is going to give me 3 du equals 6x dx. So now I've multiplied to make a perfect match to what I have left. So I'm going to replace and make the problems only have u's. So it's going to be the integral of u squared times 3 du. So in place of this 6x dx, I put this 3 du. Now I integrate. I pass the 3 out front. Should always write equals if the line equals the line that I write equals the line above it, but I get lazy and don't always do that. So I pass the 3 through, and now I'm going to use the power rule. The adding 1 to the exponent is going to make a new exponent of 3. I'm going to multiply by 1/3, and because this is an indefinite integral, I tack on the plus c. The 3 and the 1/3 cancels, and I get 1u cubed plus c. Don't need to write the 1, but I do need to change the u back to x squared plus 5, and that's going to give me my answer, and that's going to make me put a parentheses back in because I want the entire x squared plus 5 to be raised to the 3rd power. And that's it. For 8, I'm going to rewrite it with the e first. It's an indefinite integral. It has an e. I'm going to have to do u substitution because it isn't just an e to the x power. And I like having the e's written first, so I know what I'm trying to get rid of on that du step. Now I let u be the exponent of the e. Should write equals there. And this is the rewrite of the problem. It's e to the u times 6x dx. Now go through the du dx. So I get du dx equals 2x. Multiply by dx. Multiply by dx. And I get du equals 2x dx. Not good enough because I need to make the match perfect. I make the match perfect by multiplying by 3. Either I'm going to multiply by an integer or multiply by a 1 over a fraction. And this is going to give me 3 du equals 6x dx. There's a perfect match. Now I can make the problem only have u's. This 6x dx I'm going to change to a 3 du. So I can make this problem e to the u times 3 du. Pass the 3 out in front of the integral and get 3 times the integral of e to the u du. Use the e rule that it is its own integral and get 3 e to the u plus c. And then change u back to x squared to have an answer, and I don't need a parentheses. The exponent itself kind of works as a parentheses. And that's a perfect answer for number 8. 9, it's a fraction, and it's not a monomial like the first 2 fractions that we had. So I need to rewrite this so that I can get it done with u substitution, and I need to think of the denominator as having a parentheses with an exponent of 1 in order to get this to work how I need it to work. So I'm going to rewrite the problem so that it's not a fraction that has a parentheses with an exponent of -1. I should probably put that -1 in a parentheses to make it stand out. And in order to do the rewriting with a -1 exponent, I snuck in the +1 exponent. So now I can rewrite this problem as the numerator 4 times the denominator with a -1 exponent dx. Now I have a parentheses with an exponent, so it's a u substitution problem. And I'm going to write the parentheses with the exponent first. And anytime I have a parentheses with an exponent, I let u be the inside of the parentheses with the exponent. I do u substitution. That will allow me to rewrite the problem as u to the -1 times 4 dx. I'm going to use the derivative of this u to get rid of that 4 dx. For the derivative of u, I'm going to write du dx. The derivative of 4x is just 4. The derivative of 1 is just 0. I multiply to get rid of the dx's, and I get du equals 4 dx. It's a perfect match, so I don't need to do anything. Now I can just make the problem only have u's. Make this u to the -1, and then 4 dx gets replaced with du. And this is a good thing. This is the u version of the ln rule. When you have a -1 exponent without a coefficient, this just integrates to the natural log, in this case, of u plus c. Technically need an absolute value. And to get my answer, I'm just going to change the u back to 4x plus 1. And the absolute value symbol from the formula works like the parentheses, so I don't really need a parentheses. So that would be perfect for number 9. 10 is another kind of clone of number 9. I'm going to rewrite the problem so that it has a -1 exponent. I can't clear the fractions like I did in the two problems. I forget what their numbers were, but the two problems that had like an x in the denominator without any adding or subtracting. So these two problems, 9 and 10, I'm going to set them up so that they have a negative exponent by taking the entire denominator, sticking it in a parentheses with an exponent of 1, which will allow me to write the problem with a negative exponent. So have my negative exponent. I probably should have skipped right to this step, writing it the negative exponent parentheses first. Now I have a good setup. I'm going to let u be the inside of the parentheses. Rewrite the problem so that it only has a u. And do my work with the derivative to get rid of this 9dx. So the derivative of u is du dx. The derivative of 3x is 3. The derivative of 7 is 0. And I almost always, if I'm writing a key by myself, I don't show the du dx. I just do that multiplication in my head ahead of time. So I skipped a step there, but I think a lot of students will be hopefully comfortable at skipping that step at this point. I need to match up with 9dx. I have 3dx, so I'm going to multiply by 3. And I'm going to get 3 du equals 9dx. So now I can replace that 9dx with 3 du and get the integral of u to the -1 times 3 du. Now I'm going to integrate this. I'm going to pass the 3 out front and get 3 times the integral of u to the -1 du. This is the x version of the ln rule that would apply for u's. So now I'm going to integrate, and I get 3 times the natural log of the absolute value of u plus c. -1 exponents get the natural log rule. And lastly, change the u to 3x plus 7, and I'll have an answer. So 3 times the natural log of 3x plus 7. And these are all indefinite integrals, so I need plus c's for all of them. That's the end of 5.2. So far we've done 5.1 and 5.2. Let me do the problem from 5.3, and then make a part 2. So 5.3 is where we had to draw rectangles and find areas. And basically I just give you a set of instructions and ask you to find the areas using of rectangles and add them up to estimate the area between the x-axis and the graph over some given interval. In an online world, you're going to have to copy a graph. I'm going to give you a graph so that you know what the function should look like. In an in-person class, the graph's going to be on your test to mark up. So anyways, this is a graph of the function x squared plus 3, and very specifically, I want to find the area from x equal to 0 to x equal to 3 So the area that I want to find is this area beneath the graph. I'll be above the x-axis up to the graph. I'm going to do it by drawing 3 rectangles. So let me figure out where the rectangles need to go. Well, the rectangles, because I have 3 of them, I'm going to figure out how wide they need to be by using the formula b minus a over n. So the width of my rectangle is going to be 3 for b minus 0 for a divided by 3. That's going to be 3 over 3. The answer to part B, or I guess it's part A now, because I give you the graph, the width of each rectangle needs to be 1. So the first rectangle is going to start at 0. It's going to go 1 over. It's going to go from 0 to 1. The second rectangle is going to go from 1 to 2. This is probably going off my paper. And my third rectangle is going to go from 2 to 3. Let me draw the rectangles right on this graph. So from 0 to 1, I'm going to go at 1, I'm going to go up to the graph, and then over and down to the 0. And then the same thing from 2. I go up to the graph, and then over 1, and then down. And then I already went up to 3, so then over 1 and down. So part B wanted me to draw these 3 rectangles on the graph that you either created yourself, or if it's an in-person class, that you have on your paper. So I figured out how wide the rectangles needed to be. I started at 0 and I added that number. 1 is my go-to, that's what I prefer. 1 or 2, I'm not going to make fractions or anything silly. So that's the end of step B. I've drawn my rectangles. Now for step C, I want to find the area of each rectangle. And it's pathetically easy to find the area of each rectangle. Each one of these rectangles has a width of 1. The area of any rectangle is its height, its length times its width. And how do I get the height or the length? Well, I just take the number, in this case it's 1, and I plug it into the function, and in the function's x squared plus 3, so this should be x squared plus 3. So for each rectangle, I'm going to get its height, so I can find the area of each rectangle, because that's what part C wants me to do. So for the first rectangle, its height is up here. Its height is going to be found by doing 1 squared plus 3, just plugging 1 in for the x. That's going to be 1 plus 3, and its height is going to be 4. So this first rectangle, it goes up to 4 on the y-axis. It has dimensions of 4 by 1. The first rectangle has an area of 4. The second rectangle, it goes up to 7 on the y-axis. Its dimensions are 1 by 7. To figure that out, I would just go 2 squared plus 3 using the x squared plus 3 function, changing the x to 2. That's going to be 4 plus 3, which is going to be 7. The second rectangle has dimensions 7 by 1, so its area is 7. And the third rectangle, it goes up to 12 on my x-axis. It's a 12 by 1. To figure that out without a very accurate graph, I'd say the y for that is going to be 3 squared plus 3. That's 9 plus 3, which is 12. The third rectangle is 12 by 1. It has an area of 12. So the answer to part C, the areas of the rectangles are 4, 7, and 12. I'm not even writing any units, just the number is going to be sufficient. That's the end of part C. Now we move on to part D. Let's get an estimate of the total area by adding up the 3 areas. So the estimate with 3 rectangles of the area beneath the curve and above the x-axis is going to be 4 plus 7 plus 12, and that's 23 square units. So that takes us through 5.3. So the second part of the video for this practice test is going to have 5.4, 5.5, and 5.6, which are all the definite integrals. So this was the indefinite integral and then the area part, and then we'll work on the definite integrals with the numbers and the integral signs in part 2.